Good day and welcome to the first part of our discussion on Newton's method, which is a final application of the derivative we will explore. The general goal of Newton's method is to solve for the roots or the x-intercepts of a function. That is, if analytically we write out the equation f of x equals 0, how do we go about solving for x? In general, this can be an extremely difficult question, but there are special cases where we can easily solve. For example, if we have a quadratic equation, we are all familiar with the quadratic formula, which allows us to quickly and efficiently solve for the two roots. But note, we can very quickly add to the complexity of the equation. We could ask, for example, can we find any values of x where cosine of x is equal to x? And you might contest that a bit and say it's not quite in the form we want it to work with, but simply by subtracting x from both sides, you turn it into an equation of the form f of x equals 0. And then similarly, what if we had a fifth degree polynomial equal 0? Or something that was even more complicated looking yet. In either of these cases, there is no obvious approach or method that we've seen to solve for x. What we are going to investigate today is how we can use properties from calculus and introduce something called Newton's method, which will allow us to estimate a root numerically. So no, what we are going to be talking about today is not a method to find the exact value of a root, but we're going to hopefully be able to estimate it to some degree of accuracy. During a normal semester, when we were meeting in person face to face, instead of me just leading a discussion on Newton's method, what I would do instead is I would pass out a worksheet to you all that guides you through the development of Newton's method and let you kind of discover how it works on your own. And I'm not quite going to do that here, but I'm going to note that the note sheet associated with Newton's method, what we are currently looking at on the screen, is the exact handout that I would pass out to students. So I would encourage you to pause your video and give yourself at least 15 to 20 minutes and see how far you can make it through this activity, and at a minimum, let's shoot and see if we can get through the first problem. This video will focus in on the first problem, and then we'll investigate some more subtleties and examples related to Newton's method in the previous two videos. So to begin, let's look at the very simple question we have for one part A. We have a graph of the function f of x in blue, and our entire goal is to approximate where that function crosses the x-axis. So we are calling this value r. And the question is, how closely can we approximate r? So what we are going to do is start off with an initial approximation. We're going to say x1 is somewhere close to r. And I know it doesn't look reasonably close in this picture, but we need a starting point. And what we are going to do at x1 is go up to the curve, and we would have the point x1 comma f of x1. And at that point, we are going to sketch the tangent line. And where that tangent line intersects the x-axis, we are going to call this point x2. And the observation I want to make, and this is just a very kind of initial observation, is x2 is closer to this value r we are trying to approximate than our initial guess x1 was. And we will now try to solve for x2 kind of algebraically. And note, this isn't something we can solve for exactly in terms of a nice concrete number. It will, of course, depend upon x1, f of x1, and the slope of this tangent line, f prime of x1. And also keep in the back of your mind throughout our discussion what x1 represents in this problem. x1 represents an approximation of the root we are hoping to find. So it's our initial approximation. So first thing first, let's write down the equation of the tangent line. So the equation of the tangent line at x1 is going to be given by y equals f prime x1, the slope, x minus x1 plus f of x1. What we would like to do is find the x-intercept. So x2 is the x-intercept of this line. And the x-intercept occurs precisely when y is equal to 0. So when y is equal to 0, the associated x value is going to be our quantity x2. And this is where we would algebraically like to solve for x2. So the first thing we could do is subtract f of x1 from both sides. And then we're just going to proceed through algebraically doing the simplest possible manipulations we can. To isolate this x2, we need to get the f prime of x1 over to the left. So let's divide both sides by f prime of x1. And then lastly, if I want to get that x2 by itself, we will add x1 to both sides. So x2 is going to be x1 minus the quantity f of x1 over f prime of x1. And this is what we were shooting for. So note, we're trying to approximate the value of the root r. x1 is an initial approximation that we can make. We draw the tangent line to the curve and find its x-intercept, which we call x2. And the idea is that hopefully x2 is going to be a better approximation to the root. And guess what? This was so much fun the first time, you say, well, how about we do it again? So if at this curve at x2, we draw the tangent line, and we'll call where that intersects the x-axis x3. So let's see if we can repeat this process and somehow conveniently solve for x3. And now to solve for x3, we're going to play the same game that we played a moment ago. The red line that we see above is the tangent line to the curve at x equals x2. And we can write down an equation for this. Y is equal to f prime x2, the slope of that tangent line, times x minus x2 plus f of x2. And by definition, we've made x3 the x-intercept of that line. So we know that x3 comma 0 is a point on this line. So 0 is equal to f prime of x2 times x3 minus x2 plus f of x2. And I don't want to recreate all of that same algebra again, but if you were to solve for x3 and follow the exact same steps that we did on the previous page, you would find x3 is equal to x2 minus f of x2 over f prime of x2. And what we're trying to do is indicate that there is this iterative approximation scheme where we start off with x1, then x2 ends up being a closer approximation to the root at r. Then we find x3, which is even closer. And then we find x4. And we continue doing this indefinitely. But the power of the method is that at each step, the computations that you would perform are exactly the same, so we should be able to write down a nice, convenient formula. And in general, how we can think about this is we start off with our guess. We guess that we have a value x1. Once we have x1, we then have a formula for x2. It's x1 minus f of x1 all divided by f prime of x1. Then we said, okay, once you have x2, we can repeat that same process to find x3. So it would be x2 minus f of x2 over f prime of x2. So we have this nice kind of iterative method. in general, once you have xn, you can very quickly and conveniently find xn plus 1. It would be xn minus f of xn over f prime of xn. So we would refer to xn as being the nth approximation or the nth iterative in the process. And note, as long as the derivative is not 0 at xn, this formula allows you to find that next, hopefully better, approximation. And this formula that we've fallen upon is oftentimes what we will refer to, or what we will call, is Newton's method. So I'll say we call this idea, not just the formula by itself, but the entire idea is referred to as being Newton's method. And when we use this method to approximate the root of a function, remember that's what we're trying to do, is get close to this value at that root r. If these numbers x sub n that we get through our iterative scheme above become arbitrarily close to some value r as n is getting large, then we will say Newton's method converges, and it converges to the root r which we are trying to approximate. Now, in this example, we've developed this formula and idea that lies behind Newton's method, where we're trying to approximate a root of a function. What remains for us to discuss would be possible limitations related to Newton's method, and also a few concrete examples that illustrate how this works. So for that, stay tuned and take care.